a little bit more on this traffic situation, right? I think there's to understand this more in detail, what's happened there and how we really can reduce the amount of traffic. There's some very simple examples now, right? You can just lay back and say, okay, amuse me, and I will show you what we are doing here. So we have a file and we made it up by 15 chunks, right? And stored in 5 racks with 4 chunks. That has a redundancy of 33%. So imagine that now one of these racks is going down. How do you repair that? So if you do read Solomon, you say, okay, there will be a place, whether it's directly at the rack or somewhere else, that calls the others. And what do you need? 15 chunks. So 4 from one, 4 from the other, 4 from that, 12, 3, 15 from that. Now you have that. But you have to wait until you have all of that, and then you can decode into one and replace that over here. Okay? Read Solomon. So if you look at the read Solomon, there are 15 I/O processes. In the inter-rack, so what happens here? Nothing. But inter-rack, there's 15 decode, encode, so 15 by 15 matrix for the new rack as operations. Now, if you do it with RLNC, you do exactly what we showed you before, right? Everybody just sends out a little bit of data. So one chunk here, another chunk here, one chunk here, and one chunk here. So they get 4 times the pieces internally, so they call them, they recode, and then they send it out, okay? And when you have that, you can decode, and then you can put it out. Now you have what happens in the inter-rack, it's only 4 operations. That's good, right? Because this is the load that you have normally in your data center. Intra-rack, you have a little bit more operations, which is more or less the same operations, but you shift where it happens, right? So this is quite interesting. If you look at the memory, as read Solomon, here we just tested it out with Poisson arrivals of processes. If you would ask them and say, hey, give me the pieces, then you see here's one process starting, the other one is starting later, and then another one. So they're calling in, and the memory grows, because they need the full data until, like here, now they have it, now they can decode it and send it out. The memory goes down. And this is an RLNC case. There's not so much. They're coming in, and then only little data, and they will shoot it out. So this is what you have seen here as a text for you to read at home. So this is also what actually happens when process 1 starts, 2, 3 starts, when process 2 ends, and what happens over here when the recoding starts and the decoding, okay? So the advantage is quite clear. Memory consumption and random linear network coding, you will use less memory, and the workload is also less. You can distribute it over the computing over different tasks, which is also important. And you have more flexibility how to switch now your information or your files over the racks. That is now the interesting part. And what we brought here is how much traffic will you use over a redundancy level when you have read Solomon. These are the lines. They're not flexible. Right? This has only to do with the generation size, nothing very important. Here's the same generation size for random linear network coding and the field size of 2 to the 8. But what you see is, let's take the green point here. So you can say D is the number of racks, C is the fragments of the file, right? So if you have 6 racks and 2 fragments of the file, then you see, okay, interesting, right? I had 12 pieces, 10 pieces, and I have this kind of code. There's 20% redundancy now, and then I would have the same situation, the same traffic as read Solomon. If I would choose for D3C5, then I would say same traffic as read Solomon, but a different redundancy level. But here's D4C4, the same generation size 10. Now I use less traffic for even a larger redundancy level. But I can go back and say, what is with D6C5 or D7C3. Now I have a way to shift between racks and pieces in the rack. And this will define the redundancy level, but also the traffic. And of course, I would like to go down as possible. And for the larger ones, when you have more pieces, like 20 pieces, the yellow one, this is Reed-Solomon, the yellow dashed line, and the triangles are now the different RLNC combinations. Which one is optimal depends a little bit on you. What is your redundancy level, what you would like to have? Okay? Here in Reed-Solomon, by the way, it's a line, right? You can choose whatever redundancy level you want to have, and traffic will be always the same, right? Which is exactly the generation size. This is a plot. Just if you later ask me where this comes from, we can explain you exactly where these different settings are derived from, and this can be also some part in the exercise.